Right. So once again, let's see. So this is question number 27, page number 148. So level 2, exercise 2. The question is, a wire of length L meter made of a material of specific gravity 8 is floating horizontally on surface of water. If it is not wet by water, the maximum diameter of wire, the maximum diameter of wire in in millimeters, up to which it can continue to float is provided surface tension of water is given as T equal to 10 power 70 into 10 power minus 3 Newton per meter. So what is given here? A wire of length L meters. It is given as some L meters. Okay, not numerical values, not given L meters. And specific gravity and made of material of specific gravity 8. Specific gravity is nothing but relative density. You guys have to remember this. Specific gravity. Note. Specific gravity is also called as relative density. Relative density. It is defined as density of material or substance. Density of material or substance by density of water. Density of water. Water is the reference material here. More specifically, density of material by density of water at 4 degrees Celsius. So very simply we say density of what? Water, right? So here it is that relative density is given as 8. That means you can say this is relative density. Relative density, it is equal to density of material by density of water. This is equal to 8. So from this, density of material can be expressed like this. It is equal to 8. Density of material equal to 8 into density of water. You have to remember again here, density of water you have to remember. This is first point under note. Second point under note is density of water in SI units is 1000 or 10 power 3 kg per meter cube, or is also equal to 1 gram per cc centimeter cube, gram per centimeter cube, 1 gram per centimeter cube or 1000 kilogram per meter cube. So if you take, by substituting this here, you can write the density of material here is equal to 8 into density of water equal to 8 into 10 power 3 kg per meter cube. Yes, that's it. Next, that is also given. Next, it is given that if it is not filled by water, the maximum diameter of the wire in millimeters. That is very important. Density diameter in millimeters you are asked to find. The options are given in millimeters, not in meters. Be careful about that. So then the maximum diameter of the wire in millimeters up to which it can continue to float is the provided surface tension is 17 to 10 power minus 3 Newton per meter. So what you have to do is here to find the maximum diameter when it is floating in equilibrium, you have to say that the weight is balanced by band force, you can say, or it is provided by actually uh, here a surface tension force will act. Surface tension force due to this what you call because of it is floating on water. Water exerts a surface tension force. That surface tension force, if you just will act on both sides. This side is called considered as one free edge. The other side is considered as another free edge. If it is having length L, then the force due to surface tension is taken as force due to surface tension is force by effective length. Force due to surface tension is equal to L effective into T. Here L effective is nothing but 2L. 2L into T will be the force due to surface tension. This you have to understand. The force due to surface tension is 2L into T. It is provided by this here actually say is the weight. Of course, numerically equal to it is mg band force, right? So it is equal to here m can be expressed as weight is nothing but the density of the object into volume of the object. It is nothing but area of the object into length. Area of the object, it is immersed into length into g. Here density of the material into pi. The area is usually it is circular cross section is having, so area will be pi r square or pi d by whole square. But a part which is floating down is nothing but, let us say this is the immersed part of the diameter. pi into d immersed by 2 whole square into L into G is equal to L to L gets cancelled. So we'll get rho of the material into pi into d square G by 4 is equal to 2t, and simplifying this we'll get d square equal to 8t by rho pi g, at is equal to square root of 8t by pi rho g or rho pi g. On substituting these values, as t is given, T is given as 17 Newton per minus 3 Newton per meter, and the density of the material is given as 18 to 10 power 3 kilograms per meter cube. G should be taken as 10 or 9.8. So if you substitute this, you will get the diameter is supposed to be, right, uh, 1.5 mm, 1.5 into 10 to the power minus 3 meters, or it is or d is equal to 1.5 millimeter. So in millimeter it is supposed to be 1.5. So this is what you will get. So this is how you have to just carry out these calculations. Okay, this we can do some numericals. Okay, first we'll see that this can also be understood as, if a big drop of radius capital R breaks into n identical smaller drops, what should be the relation between radius of bigger drop and radius of smaller drops. You can also say, here we come across relation between capital R and n and small r, okay, into n identical smaller drops. Here you can also mention each of radius small r, each each of radius small r is, right. Right. So what you have to understand here is, if we have a big drop, if you have a big drop of radius capital R, if this is split into n smaller drops, if this is split into, right, this is split into n smaller drops, so n identical smaller drops, n identical smaller drops, you shouldn't take one small big like this or like this, and all should be identical, n identical smaller drops, n identical smaller drops, smaller drops, each of radius r small r, right, each of radius small r, right. Then what you have to remember is, volume of all these n drops is equal to volume of this drop. Volume remains same, volume remains same, volume remains same. So what does it mean? Volume of the bigger drop, volume of the bigger drop should be equal to volume of smaller drop, each smaller drop into number of smaller drops will be equal. So volume of bigger drop can be expressed as 4 by 3 pi r cube is equal to n into volume of each small drop is 4 by 3 pi into small r cube. 4 by 3 pi gets cancelled. And you will get here, you will get capital R cube is equal to n into small r cube, right. So capital R is equal to n power 1 by 3 into small r, or small r is equal to n power minus 1 by 3 into capital R. Any of these relations will make use. So now why we need this, just you can understand. So actually we are trying to find what energy required to break a liquid drop into n identical smaller drops. So here the energy is nothing but work done. So the work done is equal to change in area, surface area into surface tension, change in surface area into surface tension, right. So once a big drop, initially a big drop was there, so then it was changed into an identical drops. So here delta A can be expressed as A2 minus A1 into T, where A2 is area of n number of small drops, A1 is area of the bigger drop, area of bigger drop. So A2 minus A1 is equal to A2. Finally, you have n number of smaller drops. So n into area of surface area. Area means surface area of each drop is nothing but what? 4 pi area of each smaller drop is 4 pi small r square into number of drops n minus initially we have bigger drop, its surface area is 4 pi capital R square. 4 pi, if you take this out we'll get 4 pi into n r square minus capital R square. So here, if you want, if initial capital, the radius of the bigger drop is given. In terms of this, if you want, you have to replace the small r with capital R. Small r here, you have to take it as n power minus 1 by 3 into capital R. So depending on the requirement, let us we want in terms of capital R. So in that case it is equal to 4 pi into n into r is n power minus 1 by 3 r capital R whole square means n power 4 pi into n power minus 2 by 3 capital R square minus capital R square. So capital R square is common, take it out. It is n power 1. Bases are same, powers can be added. 1 minus 2 by 3 is 3 minus 2 by 3. This is 1 by 3. So this becomes, so the hence the A2 minus A1 is equal to 4 pi R square into n power 1 by 3 minus 1. This is A2 minus A1. Once you know A2 minus A1, this can be expressed as tension. Therefore, the energy required is nothing but the work done is equal to delta A into T is equal to 4 pi capital R square n power 1 by 3 minus 1. That's it. If it is in terms of radius, if diameter is given, you have to take it as d by 2 whole square. So d square by 4 cancel, you get in terms of diameter also. That's it. So now by making use of this, let us try to work out one question here. Okay. See, now we'll see a question number 20. Yeah. Question number 27. It is given that a liquid drop of diameter d, bigger drop you can say, breaks up into 27 drops, means smaller drops. You have to understand that identical drops they should be. Then find the resultant change in energy. Options are given as this. So what you have to understand is the resultant change in energy is nothing but work done in breaking the breaking big drop into 27 small drops, small identical drops. So work done is equal to delta A into T, it is equal to A2 minus A1 into T. So here directly can I express that expression. What is that expression? Is directly, one second. Yeah. Yes. So directly can take this as from this relation A2 minus A1, A delta T into T is nothing but this 4 pi R square into n power 1 by 3 minus 1. This relation you can use here. So the energy required, resultant change in energy. Resultant change in energy is nothing but I can take it as delta E R W. Delta E R W is equal to A2 minus A1 into T is nothing but what? 4 pi capital R square into n power 1 by 3 minus 1 into T. Here radius is not given, diameter is given in the question. In terms of diameter d we want, and number of drops are given as 27. So here to take as here r is equal to d by t, d by 2, and n is equal to 27. If we take, we'll get this is equal to 4 pi r is d by 2 whole square is d square by 4 into n is 27. Power 1 by 3 can be expressed as 3 cube power 3 cube power 1 by 3 minus 1 into t. So these 3 cancel, 3 minus 1 is 2. So we'll get this 4 gets cancelled. So we'll get 3 minus 1 is 2, right? 2 pi t d square. What is this? 2 pi td square. So which option is right? Let us see the options. 2 pi td square. First option is the right one. First option is the right one. That is the change in resultant change in energy or work done in breaking a big drop of diameter d into 27 smaller drops. 2 pi t d square. Right? That's